Recording is rolling. It is Tuesday, February 4th. All right, so yesterday I told you guys there's an AP night coming up. Does that show up well on the camera? Well, it's Thursday, February 13th, so about a week and a half from now. So we're trying to make a pitch to parents and upcoming students, maybe like 8th, 9th, 10th grade, advantages of AP. And we're really looking for AP students who can make the pitch themselves, because if other students can't hear it from you guys, that's probably better than us talking out in some ways, right? And so if you want to make a pitch to upcoming students about things you're learning in AP, getting out of AP, right, and why that might be a good choice for them, then go see Mr. JB's, right? So Mr. Davis. All right, so we got today's. I know I just wrapped up with you guys simple harmonic motion. Now, AP before the pandemic, they used to have a section on waves. They've cut that since. There are some demos I was looking back at. I think these are really classic physics demos, so I didn't want to fit these in first 2 minutes of class so that you'd miss otherwise. Right. Also, rotational dynamics. This is a quiz that most of you guys turned in over 2 weeks ago. Tomorrow's the last day. I'll take that. Otherwise, I just kind of put zero in the book so I can get it back to you guys.
Good morning. My name is Elijah Clark, and I'm a member of Row Capital. We run the fair for October 21st, 1950, South Carolina.
All right, and then today we're going to start on actually the last topic in AP. So AP has 8 units. Unit 8 is fluids. Now, I did open AP Classroom a few days back, so if you guys want to get in there and start reading those questions. But yeah, we got some demos for you guys. Got some notes for you guys. Thank you. All right. All right, so we can step back to show you guys some demos here on wait. Oh yeah.
So if this is the last unit, they're going to be a little bit more like smaller units, and then the rest of the year will be reviewed.
Yeah, guys, we're gonna take about 2 weeks to do fluids, right? And then yeah, we'll do review for a couple months. Okay? So between now and the AP exam's in early May. There's spring break thrown in there. I think there's an SAT day thrown in. Yeah, so yeah, you guys know the spring semester. There's usually a good bit of testing, right? But yeah, we'll have a few weeks to do some review, give you guys some practice AP exams. Yeah, the whole thing. All right, so going back, fill in some details, guys. The few demos you're about to see right here are not going to be on the AP exam, but good stuff to get out of an AP class while you guys are here. So, did I show this to you guys? There's 2 categories of waves. Okay, so we got transverse, longitudinal. It's transverse, the motion of the individual particles in the wave, and the motion of the propagation of energy is perpendicular. But longitudinal is a pressure wave. It's all in the same direction. It's all parallel. Okay? What do you guys think sound is? Sound is a what wave? Yeah, it would be longitudinal. So sound's this one down here. Okay? All right. So we got next. Did I show you guys constructive, destructive interference?
Yeah.
Oh, okay. Did I just show you some of these? Yeah, well, I guess we're seeing one more time anyway, right? Okay. Seems like pulses. Right through each other. Okay. Yeah, maybe you guys can see some of these. All right, standing waves. So not all waves are standing waves, but you can create standing waves. If there's a standing wave, you'll get these nodal points that don't move, and you get these antinodes that move the full amplitude. Looks like it's just standing up and down. Okay. Ooh. See if you guys figure this out. Guys, right here, how many total wavelengths is that right there? Here, guys, everybody look up here. Everybody learning this stuff? Yeah, that is 1 complete wavelength. That's the shortest amount that you could take that shape right there, copy paste it right next to itself, and it would make a nice smooth wave. But you couldn't do that with anything shorter. Okay, so that's 1 complete wavelength. Okay, how about and you guys see this node right in the middle? If I touch that node right in the middle, it doesn't actually affect the wave because it's not moving anyway, right? So standing wave. Right. How many wavelengths is that?
1.5.
1.5. Right. How about right there?
2.
Now that's 2. Right. So 1 full S shape, 2 full S shapes. Right. So that's 2 wavelengths. Okay. Go way back to the beginning. How many wavelengths is that right there?
1.5.
Half of a wavelength. Ooh. Okay. One of your thumbnail notes is labeled guitar string. I think guitar string. Right. So look at a musical instrument that looks like a strings vibrating, kind of like that. Right. Talks about there's more to that poster. So how tight you have to hold the tension and to match a certain note or something like that. It's a little bit more physics, but yeah, part of it's that. Recognize that that's half a wavelength there. All right. So it's like see Chaseman, California.
In California, and I'm gonna try to break this wine glass by only my voice.
All right, so guys, do you guys know what the physics of that's called? Right. Yeah.
If you match the same frequency as the
Exactly. Yeah. Resonant frequency. It's called resonant frequency. So here, do you guys think speed of sound is maybe different materials? Like did I tell you guys what the speed of sound in air is approximately? Yeah, 300 something meters per second. Right. Now through glass, it's some speed. It's probably faster because it usually goes faster through solids. Okay. And see if you knew the circumference of that glass right there. See there could be some sound wave set up going around. Okay. And if the frequency they was going, because it was like a single note, you sound like right. If the wavelength matches like some multiple of that circumference, then it's going to set up a standing wave, right? And if you just keeps pumping in that frequency, you hit the resonant frequency, and that's the material, right? Okay. Guys, can that happen with larger structures? Can that happen? Yeah. Who's taking ROTC? Yeah. All right. So you guys learned to march left, right. But you're told to break step where? Do not march over a. Who's that bridge? All right, winner. Yeah, don't march over a bridge, right? Can that tear down the bridge?
Military types going across a bridge. Before they hit the bridge, the honcho's going hut, hey, hut, hey, four, or step, everything. But when they get to the bridge, they break step, and then like that, and then maybe everyone crosses the bridge out of step. Why? What if the resonant frequency of the bridge is you know what I'm saying? In fact, this happened in Manchester, England some years ago. All the troops are following the honcho, and the honcho's counting cadence, and he goes across and he's ahead, and he keeps going. He's on the other side of the bridge, so and the people
All right, how do you guys feel about Tacoma Narrows Bridge? You guys ever seen this?
No.
Right. Okay, well, that's what you're in this class for. Right, so you guys get to see this. Right. So we're going back to 1940. So think kind of near the end of the Great Depression time. Right. This is out in Washington State. They built this bridge. There's opening day right there. I don't know how it's in color. I don't know if it's like extremely expensive to shoot that, or if they colorize it. I don't know.
They take the original footage and then they recolor it.
Yeah, that may be the case. Yeah, maybe it's shot in black and white originally. Right. Okay. But now opening day, it did bob up and down a bit. Wasn't really supposed to. It did. One day this happens, and of course they close the bridge. Except for now, there's one car on it, and it's kind of hard to tell. There's an engineer out here walking along this nodal line. There's an engineer walking along. He's checking this out. Now he did get off this bridge before. Well, all calamity struck. But here's some questions, guys. What is that bridge made out of? Concrete and steel. Yeah, concrete and steel. Concrete and steel bridge. Okay. How about how? Yeah. Where's it getting the energy from to do that?
The wind.
The wind. Yeah. So there's this crosswind come across. All right. So maybe a horizontal type wind. Hold on to that idea. It's gonna be there he is. You can see him better. It's walking along. Okay. How much time approximately does it take to cycle? Let me rewind a little bit. How much time to go from, say, one point back to the original point?
Is it the concrete cracking?
About 4, 5, 6 seconds. You saying? Okay. Now I've got this guy muted, but in the narration he calls it 5 seconds. Let's just call it 5 seconds, guys. If that's 5 seconds to cycle, then what's the frequency? 1/5 hertz. Yeah, about 0.2 hertz. Yeah. I bet that's the resonant frequency of that bridge, isn't it? Right. And that wind just keeps plowing energy into the bridge. Okay. see, go towards the end here.
Bro, why do you want to see me drink?
Yeah, pretty close. Yeah. Now, part of the bridge is okay. Like this column here, like that's fine. The column and right. So they did go back and rebuild this. Now, obviously, they don't want to build it exactly like they did before because that would happen again. But let's see what went wrong with this bridge and how can they fix this. Let me see if I can find a good screenshot or I can see what went wrong. Somewhere. Okay, actually right there you can see what was wrong with this construction. Right. It's right down here. You guys see these vertical girders? These vertical girders? Right? Right. So let's see, switch over. I'm gonna steal some notes from my honors class yesterday. Where's my here's my bridge. Here's my bridge right here. Oh, it's supposed to switch over. Here we go. Okay. So what the engineers were thinking when they originally designed this is, well, we've got all these heavy cars going across. We got to carry that vertical load. And what better way to carry vertical load than have a bunch of vertically oriented girders like this, which in isolation would be pretty much true, right? Okay. But in the real world, like actual environment, maybe there are other factors they weren't thinking so much. Like, oh, how about that horizontal crosswind? Right, there's a huge horizontal force that maybe these vertically oriented girders aren't so good at handling, right? Right. So when they go back and build the bridge, what's the solution? Triangles, truss system. You guys saying triangles truss? All right, got class of winners right there. Yeah, there you go. Right now, there are different kind of trusses. That is just one example, but yeah. Right, so now you can handle the vertical forces, but also the horizontal forces. There you go. Okay. Let's see. Anything else for you guys? I think. Yeah. Okay. It's pretty good there. All right. Let's see. See some fluids. Oh yeah.
I'm trying to get my
Yeah, it was the wind. Yeah, so the wind was supplying the energy.
After how much time we can draw? This silly bridge.
Yeah. Do you guys know a show called Mythbusters? Maybe.
Yeah.
Yeah. I think there was an episode they did something like that. They took like a resonator to a bridge and were like, it started to vibrate and like more than they thought it would, but didn't tear it down. All right. All right, let's do some fluids here.
The pressure is more against the bottom. What's to prevent that dam from scooting downstream? Especially when water seeps in here and you get these like little pebbles in here, like ball bearings. Why couldn't that whole dam start come downstream? It could do that, couldn't it? But you can stop it. You know what you can do? You can put a heavy weight on the top. Tons of lead. You could squash it right down, and that heavy weight would scrunch the dam right in there, and it would be held secure. But there's a better way. You don't need the big chunk of lead. You know what you do? You design your dam like this. Why? Now the water is going to push like this. Which brings us up to a little rule. A fluid will always push in all directions against an object, but all those directions will conspire to give a perpendicular force, right angles.
You catch what you just said? It's kind of the whole point of this video, right? This particular one, right? Is guys, water pressure always pushes how to the surface? Perpendicular. Right. So if you change the angle of the say of a tank or something, it's always pushed perpendicular. Right. Let me scroll back to the beginning here. Do you guys see all those little arrows? Like maybe these could be like a force on this square centimeter, or force. Right. Do you guys see how the forces build up as you go down? Maybe I should say pressure, right? Because pressure is whatever what force over area, force per unit area. Right. You guys know if you buy an American bike pump, you're pumping in pounds per square inch. That's a force over unit area. Right. And in this class, we're not going to use pounds and square inches. We're going to use say whatever what. Yeah, Newton over square meter, right? Newton over square meter. So force over area. Guys, did he draw this correctly? You guys see? All right. So some depth, there's some pressure right there. If it goes down twice as deep, that looks like twice the pressure. 3 times as deep is 3 times the pressure. 4 times as deep is 4 times the pressure. Is that true? Is that accurate? Yeah, yeah, it turns out it is. Yeah. Okay, so however much pressure is proportional to how deep.
A direct relationship.
Yep, direct relationship. Yep, directly proportional. There you go.
There's the rock under the water. There's some pressure against the bottom. That pressure pushes against the bottom with a force. There's pressure at the top. It pushes down with a force. Why am I making this arrow not so long as this arrow? This part's deeper. This part's deeper. That means there's more pressure. That means the water is forcing up against the bottom harder than at the top. Why am I making these arrows between the light size of that and that? Why? In fact, I can ask you a question, you can answer it. Why is it when you submerge something in the water, it doesn't start to just nudge sideways? You can see it. Check your neighbor. Okay, gang, let's look at it. We can see the rock is not buoyed sideways. Why? Because these forces are the same. And the force underneath is always going to be greater than the force on the top because it's deeper.
All right, so see, last video was talking about pressure. I've got a formula for that. The pressure, you guys all dive into a pool, right? The deeper you go, the more pressure you feel, right? And that's just the pressure is directly proportional to how deep you are, right? So if you're twice as deep, twice the pressure, right? Okay. What he's building up to with this one is he's building up to, see, why does something float, right? Like if you jump in the pool, why do you tend to float, right? There are pressures pushing all different ways, but why is the net effect upward, right? And it's because objects are three-dimensional. So, right, anything that's deeper gets more pressure, right? So he's talking about the direction of the push, right? Like, why does a buoyant force push you up, right, instead of like any other way? Even if something sinks, like I bet this big heavy rock is going to sink all the way to the bottom, isn't it? Right, right. But guys, suppose there's a scale at the bottom of this pool, and the rock on land weighs like 10 newtons. Do you think the scale's going to show 10 newtons at the bottom? No, it probably shows something a little bit less than that, and maybe it's like 8 newtons. Right? And, okay, so you got like 2 newtons in net pressure, something like that. Right? Because would that depend how deep it is? Suppose it's 5 meters deep. Suppose it's 10 meters deep. Suppose it's 15 meters deep. Does that scale still read the same normal force? Yeah, it turns out it does. Right? So it doesn't actually matter how deep the rock is, right? Just as long as it's completely submerged. Right? Right, so he's talking about the direction of the buoyant force. Right? I think the next video he talks about the magnitude of the buoyant force. Right. Which is, well, here, let's see, check it out.
What I'm going to do, what I hope to do, is I'm going to dunk this in the water. And when I do that, this weight reading will go down, yeah?
Okay. Now, right now, that weight reads how many newtons? 10 newtons. Oh, and I should have asked guys, that is newtons, right? Looks like a 1 kilogram mass weighs 10 newtons. Okay, so it weighs 10 newtons.
And I can kind of show you over here. Weight reading does go down. Would you say this, that loss of weight was equal to the support force?
And okay, when it's submerged, what's the tension in the string now? Ooh, more like 6 newtons, right? Ooh, 6 newtons. Hey, what do you guys think the buoyant force from that liquid is? 4 newtons, you guys think? It's like support with 4 newtons, right?
Well, no, it would be more than that, because if the weight of the water pushing down as well, then it's got to counteract, right?
Actually, that leads to a question that is going to show up on your guys' next AP classroom. Yeah, right. Now, if you're just focused on the weight itself, say if you do a free body diagram, here, I'll draw it with you guys. Let's do a free body diagram for that snapshot right there. And then, yeah, we'll get to what Luke is talking about, which actually does relate to something too. Okay. So, say you've got to take the water, make it really obvious that this is submerged in water, right? Okay. We got this weight right here. Okay. He's got a string pulling up, the actual weight, like Earth's gravitational pull is pulling down. Now the full mg is actually 10 newtons, right? And Earth doesn't actually change how much it's pulling, it's still 10 newtons, right? But the tension in the string was only showing, I'll call it F sub T for tension force, was only showing 6 newtons. Well, it's at equilibrium, right? I mean, it's not even moving, it's definitely some version of equilibrium. So there must be some other force right here called the what force? Buoyant force, aha. Right, so F sub B for buoyant force, right? And that has to be how many newtons? 4 newtons, right? 4 newtons. Okay, so 6 and 4 up balances the 10 down. Wouldn't that be true? Right? True. Right. Now, from the point of view of the water, like all this liquid water, right? Because that's easy to forget about. We're just fully focused on this object right here. right? But what about like the water? And what about at the bottom of the pool? I suppose this whole tank is like set on a scale. I'll draw a scale down here, like sitting on a scale, right? And what if the scale, but before you put the weight in at all, suppose the scale read like 20 newtons. And now you dunk this weight in. Now what does the scale read? Huh. Here, I'll do it before and after, but I guess it's gotta be backwards, right? So let's say you had just an empty tank of water. Well, you got a tank of water. Let's bring out a ruler. That's the reason I have a ruler up here, right? It's nice straight lines. Okay. But otherwise nothing in it. But let's say the scale reads 20 newtons right here. Reads 20 newtons, just 20 newtons of water. Okay. Then I dump the weight in. Okay. Now, if I was holding the weight in the air, it would have read 10 newtons, but now I dunk it in, it goes down to 6 newtons. The difference is 4. The water's pushing it with 4. Right? And now the scale that holds up the whole system reads how much? 24. It's going to read 24 newtons. Right? Right. It's kind of like you distributed some of the weight like through the water and onto the scale, right? Because the scale now has to support that extra 4 newtons also, right? I guess that too. Right. That is one of your AP classroom questions. Oh yeah.
Use Newton's third law. If the water is pushing up, then the block is pushing against it in the.
Yeah, that's a great explanation. That is Newton's third law, isn't it? Yeah, Newton's third law. Okay. So there's the water against the object, but the object also pushes down against the water, which further pushes against the scale. Newton's third law. Yeah.
Okay, but you also have the water above the object that's pushing down on it as well, which means
Yeah.
the buoyant force pushing up would need to be more than 4 newtons. That way.
Yeah, this is like a net effect. Right.
Okay.
You're right. Yeah. So there's some water pushing down on top, and there's some water on the bottom pushing up. Right. So it's down, up. Right. Yeah. But the net effect is overall it's 4 newtons up. Right. And it guys, what if you lowered this deeper into the water? Would it still be like 6 and 4? Yep. Yep. Still be 6 and 4. It doesn't actually matter how deep it is, as long as it's completely submerged. You'll get these numbers right here, 6 and 4. Right. All right. Guys good? Right. All right. Oh yeah.
Does that ratio work for even heavier objects, or like is it just?
Ooh, that's a good question. Yeah. So think about that. Let's play around the object. I think his kilogram was aluminum because it's like a big old kilogram, right? Now you guys have some other material that I actually got one right here, right? Because your guys' kilogram is like physically smaller, right? Physically smaller, right? I think I had you guys do kind of a version of this a long time ago, right? Where you dunked something in water like this, right? Guys, what if I dunk this in water? Suppose okay, it's definitely going to weigh 10 newtons about, right? If I dunk this in water, do you think it might read 6, or is it going to be more than 6? Probably more than 6. It's probably like closer to 9, I think, if I actually did that experiment right here. Probably 9, and the buoyant force might be like 1 newton, something like that. Because this is really, really dense. Guys, what about? Yeah, this is great because I haven't actually shown you the formula for this yet. It's all leading up to it. So this is a great question to ask, right? Right. Guys, what if this was like a little? What if it was like this? What if it was like this made out of like uranium or something? It's like it's so hard to pick this up. This is so heavy. This weighs 10 newtons somehow. I don't know. It's like made out of some crazy math, right? And I dumped this in the water. Do you think that the strain would still read really close to 10 newtons? Maybe like 9.9 newtons or something? Yeah. Ooh, so now the buoyant force, I mean, maybe it's a tiny buoyant force, like 0.1 newtons, but hardly anything at all. Huh. That'd be sure, right? Oh, yeah.
But also, like the surface area is distributed on.
Okay, yeah. Maybe it could be like a connecting factor. It has to do with the volume of this thing, right? So, like, if this was 10 newtons, it's like extremely heavy, extremely dense, and we got this one, which is denser than Paul Hewitts, and then Paul Hewitts was like a big old aluminum one, right? Which is not very dense, right? But it takes a lot of volume. Ooh, takes a lot of volume. Huh. I bet do you guys think this buoyant force is proportional to how much volume it occupies? I think so, right? And what if you kept making it less dense, less dense, less dense? What if you had like a, like something that wants to float? Like I bet a block of wood would even float, right? Because what if you take a block of wood, which is less dense than water, right? And you say, okay, it weighs 10 newtons if I hold it in the air, and you put that block of wood down to the water, and it might not even completely submerge, right? If it floats. Now, what does the scale read? 0, right? It doesn't at all. The string goes flat. It's just floating there, right? And I bet the buoyant force would now actually match the weight of the object if it's floating. Isn't that be true? Yeah. So the fact that this is 6 and 4 does pertain to like what kind of material the object's made out of, right? That now I bet that ratio would stay the same for different size objects as long as it's still aluminum. Yeah, I think this is aluminum. And I did also put these puzzles on your desk today. If you guys have some puzzles. If you look at number 38, there's a really key question here, right? So all these questions are feeding into this one. It says gravitational force exerted on the solid object is okay. They got 5 Newton object right here. Right. So they're just holding this object up. It's 5 Newtons. It's suspended from a spring scale. Okay, so it's going to be 5 Newtons. Okay. When the object is submerged in water, like right here, the scale reads 3.5 Newtons. Find the density of the object. Yeah. In fact, if you know these numbers, like in this case, 6 and 4, or in the textbook, like 5 versus 3.5, there is enough information just in that where you can figure out what is the density of the object. Right? Maybe you have to know the density of water, but yeah, something like that. Okay. Great. You guys good so far? Yeah.
The block is only like half submerged. Does it still read 0 in terms of net?
It would okay, yeah. Like, okay, what did you take? Like this object or this object and like half dunk it?
Yeah.
I think these numbers would probably be more like 8 and 2, maybe something like that. Right? Like if you barely dunk it in water, this might go down a tiny bit, and this buoyant force might be really, really tiny. And then the deeper it goes, it's gonna get closer to this. And when it's completely submerged, it'll reach these numbers. Okay. Yeah. All right. All right. So that's part of this, right? Yeah, it's got a lot more. So let's see what else could that force be equal to, right? That loss of 4 Newtons. You guys remember? So we're going back to here. It was 10 Newtons, now it's showing 6. So it looks like a buoyant force of 4 Newtons, right? Check that.
And that support force, we have a name for it, begins with BF. Buoyant force, okay? So the buoyant force can be seen by the loss of weight. Can't read that now, but read it now. Read it now, subtract the 2, there's a buoyant force, yeah? All right, I'm gonna do it over here in this overflow can, but I'm gonna catch the water that's displaced, and I'm gonna weigh it. Whoops. This is not gonna be perfectly accurate, okay? But note now what the reading is of just holding, it looks like a little bit more than 1 Newton.
Right. Let's pause, make sure everybody's following what's going on. Right. So yeah, some of the water here spilled out. You guys see this little overflow tube right here? So a little bit of water spilled out, so this won't be 100% accurate, but pretty close. So the empty beaker weighs 1 Newton. You guys see that? Empty beaker weighs 1 Newton. Now what he's gonna do, he's gonna dunk this in this water, and now the extra water is gonna overflow into this, minus what accidentally spilled out already, right? What do you guys think this little needle is gonna go up to about? Up to 5, right? Minus the 1 Newton weight for the beaker represents what? 4 Newtons weight of water, right? You guys think? Let's see if that's true. Let's see if that's true.
The empty cup. Now, if I dunk this in, this is losing weight, yeah? Because I'm displacing more and more water. There, now this has lost all the weight it can lose. This is still catching water. I want you.
All right. So it's getting pretty close. It's getting pretty close. Yeah, nice a little bit spill on the table. That's getting pretty close to 5, isn't it? Right. So what he's showing is the support force, buoyant force from this water holding up this weight a little bit, right, is exactly equal to the weight of the displaced water, which he caught over here. It's both 4 Newtons worth of force, worth of weight, right? Like I said, right? Does anybody know the name of that principle? Archimedes, aha! It's down here, so corner. Aha, Archimedes, right? There's a formula that goes with that. That's the principle right there, right? So say it again. The support force, the buoyant force that's partly holding this object up, is equal to the weight of the fluid that's being displaced.
Compare, how much weight did this lose? The suspended weight. And how much weight did this gain? Do you see that they're the same? And that brings us to a very important rule with fluids. And that's this, that the buoyant force that acts on a submerged object is numerically equal to the weight of fluid displaced by the object. Okay? I didn't say the buoyant force is equal to the weight of the object over here. No, it's the buoyant force is equal to the weight of fluid, in this case, water displaced by the object. Okay, we see that? That's called Archimedes' principle. Air have any weight? It turns out air has weight, a lot of weight if you talk about a lot of air. Okay, what's it go here? 1 cubic meter of air. Like this, huh? It's like about like this. Bam, bam, bam. 1 cubic meter of air, like a little small truckload, right? Has 1¼ kilograms. Okay, that's about 2 3/4 pounds. So try this tonight when you go home. Open up the fridge. Now your fridge is about 3/4 of a cubic meter. Ask the people at the house, hey, the air inside there have any weight? What are they going to say? Yeah, it's got some weight. See that big grapefruit sitting there on the shelf? Does that have any weight? Yeah. Say, which weighs more, the grapefruit or the air? Take a guess. You get about 2 pounds of air in there. And if that grapefruit's less than a 2-pounder, then the weight of air in that refrigerator is greater than the weight of, so greater than the weight of a dozen of eggs. Dozen of eggs weigh less than the air in an ordinary sized refrigerator.
Alright, so see if that's true. Guys, is there actually a small buoyant force on all of us right now? Just the fact that we're in an atmosphere? Yeah, there is. Okay. Do you guys know approximately how many how much more dense is water compared to air? About how many times? Almost almost 1,000 times. It's like 900 something. But we can kind of round to about 1,000, right? So 1,000 times more apparent. So the buoyant force, actually, even if you just hold a weight in the air and suspend it from the air, there's a tiny buoyant force which we normally just ignore in this class, right? But yeah, the buoyant force from water is about 1,000 times as much because it's about 1,000 times as dense. All right. Oh, so I bet the density of the material is probably going to play into some kind of formula too, right? So when you guys see some formulas later, yeah.
So when object's dropping in free fall, does it have a force pushing up on it?
True. Yeah. So if you drop something off a cliff, yeah, if you consider the atmosphere, yeah, there would be a small buoyant force. And probably the drag force would be even a bigger effect, which kind of ignore too. It's a little bit different. So buoyant force and air resistance are a little bit different because air resistance, like if it's in motion, has to do with how fast it's going, right? But yeah, it would have a small effect though. Right?
What is the specific gravity of a fluid?
Oh, okay. Specific gravity. Yeah, I think that term shows up on your puzzles. I think it's here. Let me Google double check. Right. I think it's say Google. Okay. I think it's how dense is it compared to water? Like I think water has a specific gravity of 1. I say specific gravity definition. All right. The ratio, yeah, there it is. Ratio of density. I think compared to water, right? So like water would have yeah, there it is, compared to water, right? So water would have a specific density of 1, right? But a better way to say that is 1,000 kilogram per cubic meter for water, right? So water called 1,000 kilogram per cubic meter, right? What do you guys think? Olive oil. Do you guys think olive oil has a specific gravity of more than or less than 1? Less than, because olive oil could float, right? What do you think? Liquid mercury. What do you think? It'd be more than 1 because it's gonna sink to the bottom, right? Right. So if you had different fluids,
The P up there, the P substance over P reference. Is that pressure of the substance?
oh, that's density, right? Yeah. So this is Greek letter rho. It's gonna represent density, right? So if you have like olive oil, so suppose olive oil, I don't know the number. Let's call it like 700 kilogram per cubic meter, and water could be 1,000 kilogram per cubic meter. Or you could take the ratio. That'd be like 0.7. Yeah.
P reference is the density of water, right?
Huh?
P reference is the density of water.
Yeah. Density of water is right there. Right. Yeah, because common fluid, could compare things to. All right.
Hi, gang. Atmospheric pressure time. Colored water, card, turn it upside down, and it stays. Now, wouldn't you think the water pressure would push the card away? But there's another pressure around stronger than that water pressure, and that's the air pressure, the pressure due to the atmosphere. The atmosphere at 20 miles high is squashing in this glass a lot more than the water's pushing down. And it pushes the card up a lot harder than it's being pushed down. And I can show you atmospheric pressure in action with these cans. I have some heated water, and the water molecules are going very fast inside there. What would happen if I slow those water molecules down? What would happen to the pressure inside the can? Let's try it and see. I'll dip it in this cold water. And another. What happened here? Reduced pressure inside, but the pressure outside, just the same. And cruncheroonie, pressure difference can be very, very dramatic.
If you want this to work at home, good thing to do is put a little bit of water in the can and then heat up the can, right? And then when you dug it upside down, because when you dug upside down, you effectively seal it, right? So however much like vapors inside is constant, right? And then the temperature plummets because it was hot. You dunk in the water, it cools down real fast, right? There's a lot of little parts to that, right? But hold on to that one because I might reference that a few times, right? Including is the amount of air pressure that we're in right now is kind of equivalent to being at the bottom of a swimming pool that's how deep? It's about 10.3 meters, right? Because if you see a swimming pool that's 10.3 meters deep, you dive all the way to the bottom, you effectively double the pressure on you from one atmosphere, because we're all sitting in one atmosphere right now, right, compared to the vacuum of space, right? 10 meters down is like twice that, right? All right. I think I got a
Physics is fun.
guys here.
Hey, we talked about wood floating, and you guys know why wood floats, because the buoyant force acting up equals the weight acting down. Isn't that true? In fact, isn't it true that anything submerged in a fluid will be buoyed up by a force equal to the weight of the fluid? Now, we said fluid and not liquid. Why? How about someone says, I can see why a fish doesn't sink, and I can see why a hunk of wood doesn't sink, but I don't see why that air-filled balloon doesn't sink. Wait a minute. If you see one, you got to see the other, because the air-filled balloon is displacing area. And isn't there a buoyant force on the air-filled balloon? And if that buoyant force is more than the weight of the balloon, what will the balloon do? It'll go up. If that buoyant force is equal to the weight of the balloon, what will that balloon do? Stay there. And if that buoyant force is less than the weight of the balloon, it will sink. So if I take a balloon, I blow it up with air, and I let it go, it sinks. Why does it sink? The balloons you see at the end of the string at the circus, honey, those are filled with helium. Okay? But why is it you blow your own up with air and it sinks? How about that air, gang? Is that air more dense or less dense than the air outside? It's a little bit more dense. Do you know why?
Oh, whoops. All right. He's going to say because the balloon has some tension, it's going to stretch, like compress the air a little bit. Okay. But even if that wasn't true, the latex on the balloon would just be more dense than air anyway. All right. Okay, let's get some moving fluids, because so far we've been talking about like static systems, right? But what if something's in motion? Check this out. Okay, now he's going to turn on this faucet. It's going to be a stream of water. It's going to be so thick. Okay, because what do you think is going to happen to the ping pong ball when it hits that stream of water? Huh? Let's check this out. Gets vacuumed in place. You guys see that? Huh. Right. So something about, do you guys think there's like a thin film of water going around the edge of that ping pong ball? Okay. And if it's vacuumed in place, would that represent a higher or low pressure? Yeah, low pressure if it's getting sucked in place, right? Low pressure? Huh. I think it's something to do with the low pressure there. Huh. All right. And I'll just say got one more demo and then I'll pull up some slides here. All right. Actually, this one's just a frame, just a picture. Right. So this is something called Venturi effect, which is the same thing as you guys saw. It's really just an example of Bernoulli principle. Right? I have two different fluids here, let's call it like oil and water. I don't know what the fluids are, but I'll say it's oil on the top and water on the bottom. Right? So so if water's more dense, it'll say on there. You guys see it's like this U shape. Right? But look, there's like this height difference, right? Which represents some kind of pressure difference. Now in this class, we're going to talk about pressure being in pascals, which is Newton per square meter. Right? It's common in some contexts to talk about pressure difference in terms of like height difference, but then you'd have to know the density of fluid, so you normally just assume it's water or something. Yeah, anyway, right? There's definitely some kind of pressure differential, right? And you can only get this if there's a flow of water going across the top. Now this actually combines some different ideas. There's conservation of flow and Bernoulli principle. You get what's called this Venturi effect here, right? So suppose you have some this oil flowing across the top. Now, guys, go from the thick pipe into the thin pipe. Ooh. Here's a conservation of flow question right here. Do you think this oil on the top has to speed up or slow down going from the big pipe into the little pipe? Yeah. It does have to speed up, right? And if you're not sure, think about this, take it to an extreme. What if this pipe on the right was like the size of the ocean? This pipe on the left was like the size of a straw, right? The ocean's barely moving, but through the straw, it's flowing pretty fast. Yeah, right. And I've got a better way to explain that too, but if you do cross-sectional area times speed, that's what's conserved. It's called conservation of flow, like gallons per minute, right? Cubic meter per second can be conserved, right? And what you guys are seeing here is, guys, where is there more internal pressure to this? Like if you're a fish swimming around inside this oil, where does it feel like there's more pressure, on the right side or on the left side? But you can see it right here. What's going to push down the right side? Is if there's more pressure on the right side. You guys see how it has to be more pressure on the right side to push down? Right? And there's less pressure on the left side because it's being vacuumed up. Huh. Right? Now you guys just said it's flowing faster through the little straw, right? Okay. So I think faster flow is going to correspond to a lower pressure. That's the only way it would vacuum up on that side. Isn't that true? Right? What if you reverse the direction of the flow? What if it's flowing left to right? Would it still be going fast through the little straw and then slower through the ocean?
Yeah.
That's still true. Still true. Right? Would this pressure differential still look probably still exactly like that? Still be pushed down on the right side? Yeah, turns out it would. Turns out it would. Right? So now you do need this oil in the top flowing, but it turns out it doesn't matter which direction it's flowing. Actually, if they didn't say flow right to left, I wouldn't actually know if it was flowing left to right or right to left. I would know it's flowing because that would result in this pressure differential. Right? I just wouldn't know which way it's flowing. Okay. All right, so I pull up my slides here. Actually, let's go back over here real fast. I'm gonna give you guys a checklist. Okay, so I was looking through you guys' AP classroom questions, just making sure that all the boxes are checked for all I got to teach. It's pretty much what I didn't teach my honors classes last few years anyway. Okay? So there's a few main ideas, and an easy way to remember them is A, B, C, P. Right now, this is actually not a good order, but it's alphabetical, so you guys can remember A, B, C, P, right? Right. So A, we'll call Archimedes principle. That's where Paul Hewitt was dunking the weight and showing like, oh, look, the fluid displaced. If I capture that, it weighs exactly what the buoyant force is. That's Archimedes principle. There's a formula for that. You guys are going to see pretty soon. Bernoulli principle. That's related to that Venturi effect you guys just saw, or that ping pong ball getting sucked into the water. Right. I haven't really set that up to explain it yet, but that's what that is. Right. So, conservation of flow. Actually, I have to explain this one before I explain Bernoulli principle. Like this one leads into this one. Okay. And then Pascal's principle has to do with equal pressures at equal depths. This is actually it's normally pressure is transmitted undiminished, right? Right? So you guys know all those. Maybe I should throw density in the mix, but if you remember that as a checklist, I think you guys can get all these fluid questions. All right, so let's go over here. Okay, so states of matter. Yeah, so we'll start real broad, right? Real broad, right? So here, you guys main states of matter, right? Normally, you guys know like solid, liquid, gas, right? And these all have definitions that go with them. So solid is right, some of them maintain its form. Liquid will maintain its volume usually, but not necessarily a constant shape, right? So it'll just fill a container, right? Now you can't. Sometimes there's some wiggle room on these, like what is Play-Doh, right? Or you can have like compressible fluids, right? But water is usually considered to be not compressible, so it'll just maintain its volume, right? But not its shape, right? And a gas wants to fill its container, right? Real loose definitions of these, right? Now, do you guys see going from left to right? You're heating up, going hotter, 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 like increasing the temperature, right? Or sometimes reducing the pressure, right? There's a play with that too, but just real general, right? If you keep heating up a gas, you can strip away the electrons from the nuclei, right? Create ions, right? Here's when I flip on these fluorescent lights, that's an example of a plasma, right? What do you guys think the sun is? The sun is a giant ball of plasma, right? Right now, if you keep heating a plasma, you can sort of like tear apart the nuclei even and tear apart the protons. You get this quark load on plasma, right? Yeah, so that's really extreme conditions there. Maybe like early universe, right? Let's go the other way. If you keep cooling a solid, you get close to absolute zero, like a billionth of a degree above absolute zero. It can take this really weird form called Bose-Einstein condensate. So, and PP's not going to ask that, but yeah, states of matter. All right. Right. I don't think this shows up on AP, but this is good to know anyway. Do you guys learn about this maybe in chemistry, possibly? Ideal gas law? Yeah, you guys learn? All right. So let's review this real fast in case you don't get to learn about it so much otherwise. This is really a combination of three predecessor laws that lead into this. I think it's called, what's it, Boyle's Law, Pearl's Law, and Gay-Lussac, I think. Okay. Anyway, but if you put them all together, this will just handle any question really. So if you look at the pressure and volume of some ideal gas, right, and multiply that together, which comes out to some number of joules, is what it works out to. It's equal to, see, the number of gas molecules, say, inside this balloon, if it's roped off, call it N, however many moles of gas, whatever, right? Here's T is absolute temperature. Now this does have to be absolute. So like if you double the temperature, guys, if you double the temperature of this balloon and the pressure was constant, what would happen to the volume? Yeah, it would also double, wouldn't it? Right. Oh, but the catch is for this temperature, you have to use an absolute scale, like Kelvin. Do that. Right. And this R is just a constant that ties everything together. So like if N is measured in moles, there's an R that corresponds to that. Right. Okay. Something good. How do you measure volume? Do you measure in liters or cubic meters? You just have different R, different constant there. Right. Anyway, see if you guys know some proportions. Right. How about this? Oh, guys, what if you have a balloon and you squeeze on the sides? Let's say the temperature is pretty much constant, but you squeeze on the sides of the balloon. Right. Would that be decreasing the volume?
Yeah.
And what's happening to the pressure on the inside at the same time? Increase, right? Do you guys see an inverse relationship between P and V? Right. All right. I know we only got like a minute left here. All right. I mentioned all these slides with you guys, but here, real fast. Tomorrow, you guys are gonna see density, Archimedes principle. Ooh, there's a formula there. Ooh, it's what Paul Hewitt was doing. We'll talk about buoyant force and pressure. Here's an iceberg classic question. Okay. Here's Pascal's principle. I got hydraulic lift going on right here. Hydraulic lift, Pascal's. We'll look at conservation of flow, which is going to lead to Bernoulli principle. Here's Venturi effect, which is just really an application of Bernoulli. Okay. Okay, and then there's some solids, but we're just going to focus on the liquids. Okay. Now, one poster that didn't quite make the list here because I made it recently. I just made it over the break. Is this YouTube, because I was looking through your questions to make sure that they were all checked off right. This is also a really classic question. This YouTube right here. Right, so yeah, this is an extra poster. Now I did put it on your thumbnails over the break, but all right. So what's going on here? Is this working? I think. Oh yeah. All right. Right. I will see you guys tomorrow. All right, guys, have a good day.